Hello, 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 hello. Hello. So I should just use a compressor. Okay. Hello. Yeah, so the voice is good. Now background noise is cancelled. Anyways. Yeah, hello, welcome back. Yesterday we did carbohydrates. Now we're gonna go with the lipids, yeah? And I should tell you before that the things we're gonna be covering is outside the syllabus of A levels too. So I'm gonna be giving you a hint when the syllabus gets out of the A levels syllabus, when the chapter, or you can say the topic, yeah? So I should start mentioning it. So we're gonna go with lipids first. So let's just start here. Let me just share the screen. And sorry. So yeah. So here we go. So yesterday we did until the murine, yeah. Now we're gonna go with the lipids as the second type of biological molecule. So here we have lipids. So basically, lipids are sometimes classified loosely as those of water-insoluble organic substances which can be extracted from cells by organic solvents such as ether and chloroform. So the thing is, due to the structure, due to the consecutive carbon-hydrogen bonds or less electronegative atoms being attached in this molecule or in this organic compound, which is lipid, this makes it water insoluble. Yeah, so it does not dissolve in water. In the chapter of water, which is gonna be after the nucleic acids, I'm gonna be explaining how things dissolve. Yeah, so until then, just you can take it like, because water being a polar substance, yeah, because it has an electronegative atom which is oxygen, because of that, oxygen attracts or surrounds the molecules which are polar too. So the polar things dissolve in water because of the polarity of oxygen. Yeah, I think it makes sense. It will make more sense in the chapter of water. So the thing that you need to memorize here is that organic solvents such as ether and chloroform, lipids are soluble in that. Yeah, whereas it is not soluble or insoluble in water. So the thing is, you can say true lipids are formed from or you can say formed by the condensation of fatty acids and glycerol, or you can say alcohol group 0. So we're going to talk about the constituents of the lipids. So the first one is fatty acids. So fatty acids contains C double bond OH, which is primarily the carboxylic group, which we discussed above here. So this group we are talking about, this one. So the fatty acids contain this group, whereas the alcohol contains the hydroxyl group, which is this one. Yeah. So the thing is, as we're talking about fatty acids, the thing is it contains carboxyl group. So it contains carboxylic group, C double bond O and OH. So this is the general formula of the fatty acids, and the R is the variable which can contain long chains of carbon, which can be CH3, CH2, and blah blah blah, CH2 here too, and these can be as long as they can. I mean, there's no limit. Yeah. One thing I want you to explain is that in those, maybe I should just draw the structure for a better understanding. So a fatty acid chain can look like this: CH2, 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 and etc. Then it can have C double bond O and H, yeah, which can be represented like that. So this is a typical you can say fatty acid chain. This CH2 can be a lot, yeah. So for example, this means that this specific chain of CH2 is 14 times before the carboxyl group, yeah. So the thing is, the important group here we have is this carboxyl group, which is involved in bonding with the glycerol, or you can say alcohol, for making the lipid. This is a fatty acid chain. So the thing that the core concept now comes here. So the thing is, sometimes, or you can say this can happen. CH2 times 14, and then C double bond O and OH. So can you find out the difference between these two structures? Yeah. So the difference is that this contains a single bond, a series of single bonds here between carbon atoms, whereas this structure contains double bonds. So because of the presence of double bonds, this structure is called unsaturated. And this one is called saturated. So remember, the structure that contains only single bonds between the carbon atoms in a fatty acid chain is called a saturated fatty acid. Whereas the structure of fatty acid in which there are multiple double bonds, they can vary in number. They can be 1, 2, 3, 4, etc. So that is called unsaturated. fatty acids. So now I'm gonna show you how they look like, how kind of like a representation of them. Yeah, so in books typically they are represented as straight line. Yeah, the saturated ones are represented as straight lines, or you can represent it like that, carbon chain here, and the unsaturated ones are represented with a little bit of curve here because of the double bond, the geometry, which is you can say discussed in the chapter of bonding. Yeah, the bond angles. So because of the double bonds, the bond angle changes, which due to which the chain bends a bit. And remember this, yeah, because this is gonna come afterwards, and this is a very important thing. So it is represented with a bented structure. So the thing you need to remember is fatty acid contains acidic group, which is carboxylic group C double bond OH, and are named because some of the large molecules in the series occurs in fats. They have general formula of R C double bond OH, where R is a you can say variable group. It can contain carbon hydrogen bonds such as CH3, C2H5, and so on. Okay. So mostly naturally occurring fatty acids have even number of carbon atoms between 14 to 22. Most commonly it is 16 or 18, yeah. And fatty acids, carbon and hydrogen atoms forming a long hydrocarbon tail. Yeah, so this is the thing that you need to memorize. These are the main points. Okay, one more concept that I should give you before discussing the formation and alcohols and stuff. So there is a word called hydrophilic, and another is hydrophobic. You can guess from the name that hydrophilic literally means water loving, and hydrophobic means water fearing. So hydrophilic is used for the compounds that have affinity with the water molecule. So water molecule. So for example, as we have discussed the concept of electronegativity, yeah? So for example, here is a compound CH, double bond O, and OH, yeah? So this compound has two electronegative atoms, yeah? One is O negative, and here is another oxygen which is electronegative, yeah? So there are two oxygens which are electronegative, highly electronegative. When this compound is poured into water, which contains H2O, which in itself is highly electronegative. Again, it is oxygen, yeah, here. So it has partial positive here, and if we put, so let me just draw it. So this is a beaker, yeah, and this is oxygen molecule here, partial positive and partial negative charges respectively. So here we pour this structure in water. So what is going to happen is this partial positive charge that is induced on hydrogen due to high electronegativity on oxygen, this is gonna get attracted to oxygen here, yeah? And it might happen that because the electronegativity of oxygen is high, the electrons of oxygen attracts its electrons towards itself, making this particular bond, very weak. And when the attraction between this hydrogen, the hydrogen which is connected to oxygen because of the weak bond, and the attraction from this oxygen from water molecule, this oxygen might lose, the bond might break, making oxygen negative and hydrogen positive. So what is going to happen is that one thing, that the hydrogen bonds are formed between oxygen and hydrogen from water molecules, and the hydrogen might break, making this thing, or you can say compound, dissolve in water, yeah? But if, for example, so this is a hydrophilic compound because it dissolves in water. For simply, I should say, the compounds that dissolve in water are hydrophilic. Or if you're gonna go in more compound definitions, then the compounds that are attracted to water, or you can say that absorbs water. For example, if you take this definition that dissolves in water, it is not an accurate definition because, for example, a sponge or a towel, they necessarily don't dissolve in water, but they are hydrophilic though because they absorb water, yeah? They have affinity with water, they attract, they form bonds with water molecules. So the thing is, the hydrophilic compounds are the ones that have affinity with water, that makes bonds with water, that are attracted to water. Whereas hydrophobic compounds, for example, CH2 and CH2 and CH3 and CH3. Now here, this compound doesn't have a high electronegative atoms, yeah? So the electronegativity between CH and CH is kind of same, yeah? So if we dissolve it in water, water is not gonna attract because there's not much electronegative difference. There's no partial positive charge or partial negative charge is induced, so oxygen is necessarily not gonna be attracted towards this molecule, making it hydrophobic. And the example we have here is lipids, yeah? Lipids are water insoluble because they don't necessarily have enough electronegative atoms that form bonds. So we're gonna go towards the alcohols now. So this is a glycerol structure, which is a kind of, which contains alcoholic group or hydroxyl group. So this is the structure of the glycerol that is present in the lipid, in a type of lipid which is called triglyceride, which is a most common lipid in our body. And this is glycerol. Now, the thing is, most of the lipids are triglycerides, and these are made from alcohol, or you can say this glycerol. Now, how does lipids form? So lipids are formed from the formation of ester linkages between glycerols and fatty acids. Now, how does this happen? We're going to discuss it. So for example, we take a fatty acid from here, yeah, and we place it here. Now, what happens is there are two OH here. Now, one H from this side and OH from the alcohol side. They eliminate together in form of water, H2O, and the bond is then formed, which is this. This is named, though, this is named ester linkage, but it is a kind of glycosidic bond. You're not going to say it glycosidic bond. It is an ester linkage because it is formed between a carboxylic acid and a glycerol or alcoholic group. But the thing after bond is similar. So we got 3 consecutive fatty acids. When 3 consecutive fatty acids are bonded with glycerol. Okay, what did I do here? Okay, now 2 and the third one also forms CH2, CH2, CH2 and CH3. So now 3 bonds are formed, and this makes a triglyceride. From the name you can tell that tri means 3 and glycerides, yeah? So it contains 3 fatty acids, and you're gonna draw it like that. This is a glycerol, and 1, 2, 3 tails here. So this is a triglyceride. Now, the thing that I explained before about the saturated and unsaturated is that if there is double bonds between carbon here, so what is going to happen is that this glycerol and the fatty acid chain deviates a bit. This is not unsaturated and this is unsaturated here. So what happens is this bending means that there are double bonds between carbon atoms, making it unsaturated compound, and this one is a saturated triglyceride. Now, what is the significance of this difference? So unsaturated melts at much lower temperature than saturated. Why is this? Because they have gaps or differences between, or you can say, you can see here that there are gaps here. Also, the unsaturated bonds are broken more easily. The double bonds breaks more easily than the single bond because the energy of double bond is lower than the single bond. So the melting point of saturated fats, unsaturated fats, is lower than the saturated fats. Let me just explain, or maybe I should just explain this particular thing in detail with logic in the part of the cell membranes. But the thing here to remember is that cells of polothermic cold-blooded animals usually have higher proportion of unsaturated fats than hypothermic warm-blooded animals. The reason is partly because the same that I told you, that it melts at much lower temperature than saturated fats. Maybe I should just write it here. Unsaturated. And here we have saturated. Unsaturated melts at much lower temperature relative to the saturated. Whereas the opposite for the saturated ones. Now here we'll take a 5 minutes break. So yeah, so let's just talk about hold on, I should just so yeah, let's just talk about acylglycerols. So acylglycerol, the triglyceride, have three hydroxyl groups which bonded with three fatty acid chains to make triglyceride, whereas acyl contains only one you can say hydroxyl group. So hold on, I should check the message here. Okay, now the thing, now these things are not included in the A levels syllabus, so you can skip the next 5 minutes. Yeah, so the thing with the saturated acylglycerols is that it is these are mostly fats and they are solid at room temperature, whereas the unsaturated ones, the acylglycerols, are oils because they are unsaturated. Now the logic behind this is that you can see here that there are gaps between the unsaturated ones. Because of these gaps, the level of van der Waals forces decreases, whereas here it is tight. Because it is tightly packed, the van der Waals forces are greater here. So because of greater van der Waals forces, there is stronger bonding here, and here is a bit weaker bonding here, and because of that, this one requires higher temperature and this one requires lower temperature. Okay, yeah, so let me just give you a bit of the structure of a bit of the fatty acids. For example, stearic acid. So stearic acid contains 17 carbon chain. Yeah, so it can be, for example, like this: HCH2 times 16, and C, you can write it in here, then CH3. So this is stearic acid, and this is saturated. Whereas if you talk about unsaturated ones, so this contains linoleic acid. So this is not included in the names of these fatty acids are not included, neither the number of them is included in the Cambridge CAIE syllabus. And this linolein is found in the seeds, or the oil in the seeds, and it contains usually 10, 11, 12, okay, 1, 2, 3, 4, 5, 6. Yeah, so it contains 18 carbons in chain and 2 double bonds. There's no need to remember or memorize this. Also, one thing additional I'm going to tell you is that the double bond is between 7th and 8th carbon and 10th and 11th carbon, so you can just skip this part. Anyways, let's just talk about another type of lipid, which is phospholipid. Now this one is very important because it is gonna help you in the next chapter, which is cell membranes. This is very important, and the basics of this molecule is gonna help you in the next chapter. So the thing is, this phospholipid molecule, or you can say compound, is formed from, this is glycerol, so this is glycerol, and just like we saw in the triglyceride, similarly it is bonded with the two fatty acid chains. But the key difference here is that it is not connected to the third fatty acid chain, but rather connected with another compound called choline. Now, the A-levels or Cambridge syllabus does not include the structure of choline. Yeah, so it is not required, but I'm gonna still you can say draw for your convenience. So it is a phosphate group, more specifically P double bond O here and a single bond and another one O here, and here we have got CH3, CH2, CH2, nitrogen with CH2 thrice. So this whole molecule is called choline, and this is what makes or give a special characteristic to phospholipid molecule. Now what is that? We're going to discuss further in detail in the next chapter, which is cell membranes, but here I'm just going to give you an idea what is this. So this is glycerol, these are two fatty acid chains, it is unsaturated, and here we have a choline group. Now, as you can see here, this choline molecule is charged. It contains nitrogen here, phosphate here, and this nitrogen is very important because remember what I told you yesterday, nitrogen is involved in you can say hydrogen bonding. It is a electronegative atom, and here it has a charge. So the thing is, the triglyceride molecule was insoluble. Yeah, as I told you, it was insoluble in water because it had no affinity with water. Similarly, this part present in the phospholipid is, you can say, insoluble. It's insoluble. Whereas this part, the choline one, I should write it, choline, this choline part is soluble, and you can't really say soluble, but you can say it is hydrophilic, which means that it is attracted to water molecules. Now, what happens if we put a phospholipid compound in water? So because the had being water soluble, or you can say hydrophilic, if we put a lot of phospholipids here, so what happened is these phospholipids joins together in circular form, because the head part of these phospholipids are water loving, but the tails are water hating, or you can say water fearing, if we take literal meaning. So what happened is, because these tail region, or this tail region is hydrophobic, so they are water hating, so they merge together, whereas the head part, which is hydrophilic, loves water, this merge together, forming a spherical shape. Now this is an important characteristic you need to remember. Anyways, let's just move forward. So we've discussed the we've discussed the phospholipid. Now these are extra points that you can that you need to know. These are extra, not necessarily for A levels, but for the preparation of, you can say, examination or entry test. You need to remember this, that triglycerides are part of the composition of myelin sheaths that are surrounded that surrounds nerve fiber. Myelin sheaths, you're gonna read about it further if when we go towards the coordination and control chapter. But the thing is, it is surrounded for providing insulation and providing increased speed of transmission of nerve impulse, and for the energy source in the you can say myelin sheath, or you can say, we're gonna study about it, no different where myelin sheaths and stuff like that. But it is also a part of adipose tissue below the skin, which acts as a insulation against heat loss, and it is insoluble, as we have discussed. So osmotic potential of blood is unaffected because of it. And what is osmotic potential of blood? You can say, when there, so for example, we have 1 liter water here. So the osmotic potential is the saturation of water. The pure water has 0 potential. Yeah, it is pure. But when we start adding sugar, which dissolves in water, the potential is going to decrease. Yeah, and the water potential is going to decrease, and the saturation is going to increase. So because of that, the water potential decreases to minus, 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 and so on. So because of this decrease in water potential, the saturation of sugar increases and the water becomes thick. Yeah, but if we add a insoluble compound like sand here, silicon dioxide, the sand just, you can say, accumulates at bottom. The water, you can say, water potential is unaffected, and the saturation is 0, and the water remains as it was. So this is what happens with triglyceride. Yeah, it does not affect the osmotic potential of blood. Now the triglycerides, or I'm gonna, you can say, repeat the points of triglyceride, a review for you guys. Triglycerides are the most common lipids in nature and further classified as fats or oils. according to their state at 20 degrees Celsius. The higher proportion of unsaturated fatty acids, the more likely they are to be liquid at temperature 20 degrees Celsius. Triglycerides are nonpolar, so they does not dissolve in water as they are hydrophobic. They are less dense than water, therefore floats. Their length vary according to fatty acid chain. A major function of lipid is to act as energy store or reservoir. They have higher caloric energy value than carbohydrates. Now this point I need to explain a bit. This is because they have high caloric energy, you can say, than carbohydrates. This is because of the presence of high proportion of CH bonds between them. So CH bond has high energy release when it's broken down, and because of the presence of high proportion of CH bonds between them, they have a higher caloric energy value. Okay, so animals store extra fats when hibernating, and fats is also found below the dermis of skin of vertebrates, which serves as an insulator. When fats are oxidized, water is produced. The metabolic, you can say metabolic waste can be useful for desert animals. That is why they store fats. Now, one thing, there is a misconception that I used to also have. Now, as we know, camel has a hump at the back of his body. Yeah, this hump. So when I was told that camel can survive 30 days without water in desert, I used to think it stores water in this hump. And what I used to visually, you can say, think of is that they have a small space here which they drink water and save here. But it is definitely not the case. The thing is, because they store fats in this hump, so what happens is, this is, for example, a triglyceride molecule. So breaking or hydrolyzing a triglyceride molecules will wait, hold on. Let me just confirm this. Or let's just leave it here. Anyways. So the thing is, animals store extra fats just for the reason, and you can say camel store fats in their hump primarily as a water source rather than as energy source. Why? Because, as we have seen, for producing a triglyceride, 3 water molecules have been released. As in the case of carbohydrates, one carbohydrate bonded to another carbohydrate. This represents carbohydrate, and this represents carbohydrate. So disaccharide formation required one H2O molecule. Yeah, it releases one H2O molecule, whereas fats, the formation of fats releases 3 water molecules, which helps 3 water molecules from one organic molecule. This helps camels to store fatty acids and glycerol and use them and merge them to form fats when water is required. Yeah. It also helps as insulation in animals. Triglycerides provides insulation which avoids heat loss. So yet helps the animals living in the colder regions to survive. Also, the low density of fat tissue increases ability of animals to live more easily, or you can say float. For example, whales whales contains high amount of fats, and because of the less density of fats, this allows whales to swim, or you can say float easily in water. It also protects the you can say tissues. For example, the adipose tissue in mammals lowers the risks of damages to the organs. It is like a covering on, you can say, the organs of mammals. So now we have discussed phospholipids, we have discussed triglycerides. Now we're gonna talk a bit about glycolipids. So this point is you can say included in the Cambridge, so you need to listen. So glycolipids are the association of lipids with carbohydrates forms a polar head. So these are also having a hydrophilic head. It is kind of like phospholipid, but instead of choline, the carbs chain or carbohydrate chain is attached. So the visual representation is like that. It's similar to phospholipid. It has two fatty acid chains, and one, instead of choline, it contains carbohydrates chain. So this is a glycolipid. We also have a nucleoprotein, but it's in the protein part, so let's just leave it. Okay, now the thing we're gonna discuss is not in Cambridge. It's useless for Cambridge, so you can continue till the part of protein, which is next. So the things that I'm gonna be discussed, these are important for the you can say next you can say entry test examination. So we're going to talk about vexus, which is a kind of lipid. We're going to talk about trypanoids. Hold on. So yeah, we're going to talk about trypanoids, the tryptines, steroids, carotenoids, and we're going to talk about prostaglandins. So yeah, so vexus, they're esters of long chain monoalcoholic and long chain fatty acids. So you need to memorize this. So unlike in acylglycerol, we usually have 3 fatty acids and 3 alcoholic chains attached. In vexus, what we have is long chain alcohol, which only contain monoalcohol, which, for example, you can see here, they're not 3 alcoholic groups. So here we have COH and CH2 and CH2 times 28 and CH3. So this is a monoalcohol because it only contains 1 hydroxyl group, and this is called tricontanol. So the thing is, this is a monoalcohol, and then it bonds, or you can say reacts, with the palmitic acid, which is a kind of fatty acid. So this is palmitic acid. It is saturated, and the bonding between them is esteric bonds. The result of this is the formation of ester bond, and the result is the formation of wax. Yeah, so this is how wax are formed. So these waxes are simple lipids and found as protective coating of stem, stalks, and leaves, petal, fruit skins, animal skins. You can say it is found in fur too and feathers too. Okay, so these are water repellent. You can say non-reactive or hydrophobic because of their non-polar regions, because it doesn't contain choline or stuff like that which reacts with water. Yeah, so any polar group is absent here. So it's non-polar hydrophobic compound. This is chemically inert and resistant to atmospheric oxidation. Now there are two types of waxes: natural, like you can say beeswax or cutin from the cuticle of leaves. This can be extracted, or you can say synthetic waxes, which are generally derived from petroleum, or you can say polyethylene. So this the synthetics ones are derived from by the techniques of organic chemistry, and they are from petroleum and other fossil fuels. Well, for example, polyethylene too. So waxes are considerable commercial importance. They are very important commercially because they act as a superior machine lubricant. The lubricants that you used and uses in your machines, these, because of their water repellent nature, they are used as that. Sperm whales, in the past, sperm whales were the principal source of these waxes until we have synthetics one. Now let's just talk about another type of lipid, which is trypanoid. So trypanoid is large important class of lipids. And it is made from subunits or made up of isoprenoid units. Isoprenoid units. So let me just draw a isoprenoid unit. So basically this is a isoprenoid unit. This one unit is isoprenoid unit. Now, multiple isoprenoid units, as we have discussed before in the last video, that the polymer is the combination of many monomers. The monomer here is isoprenoid unit. The combination of these units forms terpenes, steroids, carotenoids, and prostaglandins. So there are four main, you can say, types of terpenoids. Terpenes, from terpenoids, these are types of terpenoids. Terpenes, steroids, carotenoids, and the last one is prostaglandins. So these all are formed from these all are the example of terpenoids, and these are formed from isoprenoid units. Now let's just talk about terpenes here for a bit. So terpene are type of terpenoids which contain fewer isoprenoid units like diterpene, triterpene. These small terpenes are volatile in nature. And produce special fragrance. Some of these are used in perfumes. You can say mycerin, geranol oil from rose, limonene from lemon oil, methanol from peppermint oil, some components of vitamin A1 and A2 chlorophyll molecules, as well as some other molecules which utilizes in synthesis of rubber and latex. So terpenes are involved in all of them. But the thing that you need to remember here is that these contain fewer isoprenoid units. Now moving on to steroids. So steroid is a type of terpenoid which forms steroid nucleus made up of isoprenoid units, contains 17 carbon atoms arranged in 4 attached rings. 3 of them are hexagonal and 1 is pentagonal in shape. So let me just give you a visual representation of how it looks. Isoprenoid units attach together to form rings, and these rings attach with each other to form steroid. And this is how a steroid looks like. One, two, three, and here is the 4th one. You don't need to remember the numbering, but I am writing it for the reference. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So these 17 carbon atoms arranged in 4 ring, yeah? Now, steroids are similar in structure. Like for example, you can say all the steroids contain this molecule, but they differentiate with each other from each other because of the radical attached to them on the side chain that distinguishes them from one another. For example, cholesterol is one type of steroid. You can say estrogen and testosterone are other types of steroids too, but let's just take the example of cholesterol. Cholesterol contains side chains, for example this OH, CH3 here, CH3 here, and on the 17th carbon a group of CH3s and CH2s. So you get the point. You don't need to remember it, but the thing is, this is the structure of cholesterol, yeah? CH, CH2 thrice, CH, and CH2 CH3 twice. So this and CH3. So this is exactly the structure of the cholesterol. Because of these side chains, there is differentiation between other steroids. But remember, the parent structure, or you can say the core structure, which is similar in all of the steroids, is this: the steroid skeleton. Now, let's just talk about carotenoids. And after that, we're going to be talking about prostaglandins, and this part of the chapter ends. Let me just drink water. Now about the carotenoids. So carotenoid is a polyterpenes, or you can say polyterpene. So terpene was made out of isoprenoid units, diisoprenoid, few isoprenoid units, you can say diisoprenoid, triisoprenoid units, you can say multiple. So the thing that I want to say is that terpenoids, or you can say terpenes, were made from few terpenoid units, which is made from isoprenoid units. So terpene is made from terpenoid, and terpenoid is made from isoprenoid units. And from terpene, multiple terpenes, polyterpenes, is made carotenoids. Yeah, so it is polyterpene. Yeah, and it consists of long chains of isoprenoid units which contain isoprenoid rings at both ends of the terminals. So the compound carotenoid are mostly pigment producing. Yeah, so red, orange, yellow, brown, these are present in plants. The carotenoids are, you can say, pigments that are present in plants for absorption of light spectrum. Some important carotenoids in the plant pigments are like chlorophyll, cytochromes, phytochromes, and it is present in latex and rubber too. So I shouldn't be drawing the structure because it's not necessary here, but okay, I should just draw it anyways. Just so this is what kinda how a carotenoid looks like. This is the structure of beta carotene. So the thing that you need to memorize is what isoprenoid units make terpenoids make terpenes, and terpenes, multiple terpenes, polyterpenes, make carotenoids. And the you can say characteristics of carotenoids is that they form the pigments. The compound that are pigments are formed by carotenoids, and these can be the pigments, for example, red, orange, yellow, brown in plants. And the important carotenoids are chlorophyll, cytochromes, phytochromes, which we'll talk about in bioenergetics chapter. But this is the thing. Now let's just move on to prostaglandins. So prostaglandins is not required much for you to know, but as just let me just explain you on the surface that prostaglandin is a group of lipids made by mammalian tissue at sites of tissue damage or infection that are involved in dealing with injuries and illness. Yeah, they control different physiological processes, you can say, such as inflammation, intensity and sensation of pain, blood flow and formation of blood clots, immunity and induction of labor. These are the things that involves the physiological, you can say, effects of prostaglandin. You can say it is a kind of hormone. So we use aspirin to reduce blood clot, you can say the fever, and decrease pain depends on the inhibition of prostaglandin in its synthesis. Yeah, so we're not going to be talking about the structure of prostaglandin here, because it is neither necessary and it is not, I've never seen it, its structure in books. So the thing is, prostaglandin, you just need to memorize, is a group of lipids made in mammalian tissue at sites of tissue damage. They control different physiological processes such as inflammation, intensity and sensation of pain, blood flow and formation of blood clots, immunity and induction of labor. So they control different physiological processes such as inflammation, intensity of pain, blood flow and formation of blood clots, immunity and the induction of labor. Anyways, let's just not write it. So I'm feeling a bit dizzy right now, so I don't think I need to write that much. Anyways, I've repeated multiple times. I will repeat it once more for you to write. So they control physiological processes such as inflammation, intensity and sensation of pain, or you can say intensity of sensation of pain, blood flow and formation of blood clots, immunity and induction of labor. So, and they are involved in dealing with injury and illness, and we use aspirin usually to reduce the concentration of, or the synthesis of prostaglandin to decrease the pain. Anyways, this here are lipids, and this is enough for you to know, I think, for the lipids part. Now we're gonna move towards protein, which is a big chunk of this chapter. And if we are able to complete protein today, only nucleic acids will be left, which we'll discuss a bit in this chapter because the main chunk of it is in the genetics. So we're just gonna talk about the structure and bonding and stuff at that place, and we're gonna go with water, and the chapter is done. Anyways, a 5 minutes break, then we will continue with the protein. Oh. To drink some water. Okay, I think it's 4:16 a.m. here. So the stream is around 1 hour and 30 minutes, 18 minutes now. So I think we should do protein tomorrow, or you can say protein plus nucleic acids tomorrow. We can leave this topic because today I was a bit late with the stream. So tomorrow we would be able, I hope we would be able to do the streams, or maybe on the next weekend we will end this chapter. We will do protein and the nucleic acids tomorrow, maybe, and then water too. So another class will be required for this chapter to be completed. So I think it's enough for today. Yesterday we did some basic concepts of chemistry. Then we did carbohydrates, and tomorrow we'll do protein and nucleic acids. Because the thing is, I'm feeling very dizzy right now. I need some sleep. I need to go to have some sleep. So we will start the stream tomorrow early so we can continue with protein, and we will have 2 hours of stream. We'll complete protein and nucleic acid in it, with including with water from all of these syllabuses, and then we will go towards the next chapter. But and the next chapter is going to be cells. Anyways, let's just continue with it tomorrow. Until then, bye bye.